Welcome back to 15-Minute Math. So today we're going to continue on our quest to find areas under curves. And remember, when I say area under curves, really what I'm talking about is the area between the curve and the x-axis. And we've been doing that basically by drawing in rectangles under the curve and finding the area of those rectangles and just kind of assuming that the area that we get by adding up those rectangles is approximately equal to the area under the curve itself. We know there's a little bit of error, but we've been saying that for most purposes that's pretty much good enough. And we're going to kind of build on that, and what we're building towards is a way to kind of mathematically, in a mathematically rigorous way, to use infinitely many rectangles and take that error down to zero. We have noticed that the more rectangles we use, the smaller the error. So the natural conclusion is that if we can use infinitely many, there's going to be zero error. And in fact, that's true. But before we get into how and why that works, we really need to kind of build some notation and some techniques that are going to take us there. So in order to demonstrate that, we're going to use this example that we see on the screen. So we're going to estimate the area under the curve 9 minus x squared on the interval 0 to 3 using 6 subintervals. And I'm going to use right-handed endpoints. So the right-handed rectangular approximation method, as we've been calling it, which is to say I'm going to draw my rectangles until the right-hand sides hit the curve and then draw over. So first of all, remember we had this formula that said interval lengths, or maybe I should say subinterval lengths, is going to be given by b minus a over n, where that right there would be our b, the starting point of our interval is a, and the number of subintervals is n. So in this case we have 3 minus 0 over 6, or 1/2, which tells me that each interval is going to have a length of 1/2, each subinterval I should say. And so I know I'm going to have a rectangle here that kind of spans this area. I'm going to go up until the right-hand side hits the curve. Boom, there we go. Draw straight over. So that's one rectangle. And then I'll do the same thing here. Do the same thing here. Not very good at drawing straight vertical lines, it turns out. We'll do the same thing here. How many do I do? 6? 1, 2, 3, 4, 5 would be about there. And then 6 is one of those degenerate rectangles, so the right-hand endpoint starts off on the curve, so really it's just kind of flat line on the x-axis there. And we can see this is going to be an underestimation, right? Because there's area here, 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 here that's not accounted for. So we know we're going to underestimate. This is not going to be the true area, but it's kind of sort of close. And we can always start to use more and more and more. I just like to keep it somewhat small to keep our computation somewhat small. And really what we want to focus on today is how to represent these summations with what we call summation notation. It's going to be very handy to be able to do that. But before we do that, let's just kind of do what we've been doing, just maybe kind of get a feel for, or maybe just remind ourselves what this process is like. So notice we've got 1, 2, 3, 4, 5, and kind of 6, I suppose, rectangles here. And we said that the estimated area is simply going to be the sum of the area of rectangle 1, the area of rectangle 2, so on and so forth. And in order to find the area of these rectangles, really what we need to do is we need to find the width 1, height 1, right? Because the area of a rectangle is just the width times the height. And that would be width 2, height 2, plus width 3, height 3, dot, 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 till we get to width 6, height 6. So we're just continually taking width times height, width times height, width times height. And I can actually do us one better. Actually, you know what? Maybe we should just pause there. So that's what we want to keep in mind, and we would just add these numbers up and we get our answer. Now remember, width is going to be 1/2 in this case. That's the length of our subintervals. And the height is found by taking function values. And so maybe actually that could be worth writing. So that'd be 1/2 times f of 1/2 plus 1/2 times f of 1 plus 1/2 times f of 3/2 plus dot 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 till we get to 1/2 f of 3. And the idea is this: if 6 rectangles, it's really not that bad to write, but I've already started to kind of shorthand things, as you can see with my ellipses there. Imagine if we were doing 12 rectangles, 24 rectangles, 48 rectangles. It gets a little bit absurd to write all that out. So what we need is some shorthand notation, and what we're going to use is what we call sigma notation or summation notation. So sigma notation, you may have seen before, uses Greek letter sigma to represent sum. I guess S for sigma, S for sum. Now remember how this goes. On the bottom part here, we kind of put the starting point of our summation. At the top, we put our ending point, and then out here to the right, we put the rule of what we're actually going to be taking the sum of. So let's try to express this in generality first, and then we'll kind of make it specific to this example. So we're going to sum from the first rectangle all the way to the 6th rectangle. And what are we summing? Well, we're going to sum the areas. So I guess we could just say like A sub n, and that would be our estimated area. Right? That pretty much encapsulates what I mean. We're going to start at A sub 1. That's where we start. And then you kind of just run in upwards and upwards till you get to 6. Next we'd have A2, A sub 3. We just keep running in upwards and upwards, and we know when to quit when we get to 6. That's how we know where to quit. Now, that's all well and good, but it's not very telling, I guess. Like A1, what is A1? What is A2? You know, how do I find the area of these things? It would be nice if maybe this symbolic notation gave us a little bit more information about what we were actually doing. So maybe a little more explicit would be to write this. We're going to take the sum. We're going to start at the first rectangle. We're going to end at the 6th rectangle. And we're going to take width n, height n. And if we do kind of like what we did here, we would end up with exactly this line here, which is a little bit more descriptive. Width times height, width times height, width times height. But I'm going to claim that we could even do better than that, because we can describe the width of this interval. In fact, this interval has a width of 1/2, or I should say the subintervals have a width of 1/2. But even more generally, we could write that formula that we know, b minus a over n. And actually, I'm running into some clashing variables here. If I'm going to use n here, I can't really use n here. So maybe we should just go ahead and call this k. And I'm just going to make a note over here. K equals the number of subintervals. We were using n to do that, but now I'm using n here, so you can't really use n twice in the same expression to mean two different things. So there we go. We'll just use k there. Okay, and then what's the height of each of these rectangles? Well, let's remember how we did this. We drew upwards until we hit our function. So the height of this one is just f of 1/2, and the height of this one is just f of 1, and the height of this one is just f of 1.5 or 3/2. And it's kind of important to note that we started this whole thing at 0, or the very start of our interval. Remember, in the generic sense, we just called that A, because remember, this interval here was just like from A to B. And so in this case, A is 0, but of course, it doesn't always have to be that way. And so let's think about what we were doing. We were starting at, well, the start of our interval And we're just kind of jumping over the width of a subinterval and then going up and finding our function. We're going to jump over the width of a subinterval, go up, find the function. And so one way to describe that would be to say f of, well, we start at a, the start of the interval, and we're going to jump over by the width of a subinterval, which we already know this expression describes the width of the subinterval. And we're going to do that every time we move on to a new rectangle, and so we'll just, every time, we'll increase n by 1. And so that right there is the generic form of how to get an estimate using rectangles and how to represent it in summation notation. Now keep in mind, this is for, remember we're doing the right-handed approximation method. So that might look a little different if you're doing the left-handed approximation method, because the very first rectangle, you don't have to already move over the width of that rectangle. Remember, if I'm doing the left-handed approximation method, I'll do it in green. I would go over until the left-hand side hits my function. And so I wouldn't start at f at 1/2. I'd start at f of 0. So thinking about how you could represent this thing here would be a little different. And I know this looks crazy complicated. And it kind of is, and especially the first time you see it, it definitely is. But just keep in mind, this right here just represents the width of each rectangle. And this right here just represents the height. We're still just finding width times height. We're just kind of representing it in the most general sense for a right-hand approximation. And now let's go ahead and let's apply it to this specific example. So in this case, b is 3, a is 0, k is 6. I'm going to put parentheses here just for clarity. And that's going to be f of 0 plus 3 minus 0 over 6 times n, which is, well, 3 over 6 is 1/2 times f of, again, this value here is just 1/2, so it's just going to be 1/2 n. And now we can make this evaluation. So if I let the sigma notation do its job, first I plug in 1 for n, so I have 1/2 f of 1/2. And then I up n by 1, so I'd have 1/2 f of 1/2 times 2 is just 1, plus 1/2 times f of, now n is 3, right? This here was n equal 1, n equal 2, n equal 3, so that would just be 3/2. And then we would have 4/2, which is 2. And then n goes up to 5, so we have f of 5/2. And then we have f of 3, right, 6/2. And I think just to get a sense of closure, we ought to actually evaluate this. Recall that the rule for our function is 9 minus x squared. So when I plug in 1/2, that's going to be 9 minus a quarter, or 8 3/4. So I have 1/2, 8 3/4, that's 35/4, plus 1/2. Plugging in 1's easy, I'm just going to get 8. Now I have to plug in 3/2. I get 27/4. If I plug in 2, I should get 4, so that's going to just be 9 minus 4 is 5. Now 5/2, let's see here. Should get 11/4. And the last one's easy. We end up with 0. So now it's just a matter of adding them all up. I will do that really quickly. I got 125 over 8, which is, for you decimal lovers out there, about 15.625. Actually, it's exactly 15.65. That's not repeating. So I've reached my 15-minute time limit. Next video, we're going to move on and go for infinity.